today I'm going to be talking about modern DI security proofs. And this is basically a merging of two works. So the first is on the Rényi EAT, and the second is how you use it for DI security proofs. So the outlook for today's talk is relatively straightforward. First, I introduce the Rényi EAT, then I'll talk about Petz-Rényi divergences, and then I'll join them together to show how you create DI security proofs. And then I conclude. So first, I want to talk about EAT channels and previously known results, and then I'll introduce the Rényi entropy accumulation theorem. So the picture you should have in mind here is that there's some bipartite state. You hold one part of the system, and an adversary holds the other. This is the quantum side information. Now, if you want to generate random bits with this, you need to implement some channel on your system. So these kind of channels generate two types of data. It'll generate private data. These are the bits you want to keep hidden. And it'll also generate public data. This is the data that you're okay with being broadcasted during the protocol. And if you want to generate more than one random bit, you sequentially apply these channels. So you apply an M2, M3, and so on until you've generated n random bits. And the question that we want to ask is how random are the bits an if someone has the quantum side information E prime and the public data in. In other words, we want to bound the smoothman entropy of an given E. Also, a closely related quantity is the up arrow sandwiched in the entropy. They both quantify basically the same thing. So depending on which quantity makes the results look nicer, that's the one I'll be using. A small caveat, at the moment we have no restrictions on the input state. So the bounds that one generates in this setting are generally trivial. Maybe to motivate this a little bit from a QKD perspective, it's not that we care about any specific state, it's that we want to find the worst input state. And so you can imagine if we don't constrain it, then there exists totally deterministic states that generate no randomness. So how do we constrain the state? Well, typically this is done via some kind of test. So in every round, we generate some additional test data. And for the purpose of this talk, the test data will take one of three values. So 0 and 1 basically mean you fail or you pass the test. And this perpendicular sign just means that you didn't do a test at all. So for most rounds, we won't be doing a test. So this is highly skewed towards this perpendicular symbol. And now we say we accept the protocol. We say everything succeeded if the witness test distribution lies inside some accepted set. So what was previously known about this? Well, EATs generally have the following structure. So here we have the smoothman entropy over the whole protocol, and we say it accumulates linearly, where this is some single round contribution, and then you have some second order terms that are a little bit too complicated to write out. For those wondering why it's not just an here, but also the test data, this is a quirk of EAT proofs, but as I said, S is usually very skewed towards the perpendicular sign, so most of the randomness really comes from an. And how should we understand the single round quantity? Well, it's the von Neumann entropy accumulated over a single round. Here M is the worst channel that we've applied, so it's the worst case setup. And then we input to this channel some state sigma, and the only constraint we have on it now is that M acting on sigma generates an acceptable test data distribution. However, the second order contribution, even though asymptotically it disappears, is really not negligible for practical implementations. So even if you do 10 to the 7 many rounds or 10 to the 8, this term will either dominate or be comparable to the first order contribution. So if we want to kind of decrease this error, we need to understand where this error is coming from. And in part, it's coming from the fact that we're using the von Neumann entropy for the single round quantity. The way I like to think about it is that for asymptotic behavior, the von Neumann entropy is the perfect quantity, but when you want to use it for finite size analysis, then you incur some penalty terms. So in other words, we think that it's much more natural to consider single round Rényi entropies, which cause much less error correction terms. So now let's talk about our result. So our result can be written in this way, and you already see the second order contribution is really easy and can be written out. This also appears, by the way, in the original EAT. This is one of the many contributions. Now the single round contribution here takes this slightly more complicated form, and to really understand it, let's compare it to the original EAT. So the von Neumann entropy gets turned into the down arrow sandwiched in the entropy of a single round. And the main difference is here M and sigma are not constrained directly in any way. So here in the original EAT, they have to satisfy some test data distribution. Here they just generate some random distribution P of S. So how do we constrain it? Well, here Q is the accepted test data distribution, and if P is close to Q, then this term is 0, and if it's not close, then this acts as a penalty term that kind of constrains the system in a soft way. And the only other term I didn't mention is this Q perpendicular. This is the type of, this is the behavior you'd accept, and this is the probability of not having a test round. This is close to 1, so you can kind of imagine the 1 being here. Some notes. First of all, as I mentioned, the second order contribution is much simpler. Also, for those that have worked with EAT proofs, technically this is not what it's saying. There's some min trade-off function, which is hard to calculate in general, or at least very tedious. Our bounds do not have this whatsoever. We get rid of min trade-off functions completely. So what you see here is what's actually the relevant thing. And lastly, as a function of sigma and Q, this is a convex optimization problem. So for device-dependent QKD or DIQKD, this allows it to be solved efficiently. Now let's talk about the second part, namely Petz-Rényi divergences. Here I'll show how one can bound them and how one can use these bounds for DIQKD. So Petz-Rényi divergences are of this form. Most of you have probably seen it already. The most important part here is that both rho and sigma have exponents attached to them, and these are the things that cause complications. So the bounds that we generate are of the following form. Here you see that alpha and 1 minus alpha have totally disappeared, and instead we've included some polynomials p and q. Z here is some linear bounded operator that we optimize over, and then these are just polynomials of them. I should point out that we have 2 of them. One is generally new, and the other one is based on work by Peter Brown, where they do it for the von Neumann entropy. The newer one has some additional properties I'll talk about soon. So why do we care about this structure? Well, first of all, upper bounds on Petz-Rényi divergences lead to lower bounds on Petz-Rényi entropies, which is what we want. And second of all, although a little bit more complicated, is that this kind of structure is exactly suitable for applying the MPA hierarchy. So these bounds are also useful in a DI setting. Now, some additional properties. Here, if alpha is between 0 and 1, then one can choose P and Q to be positive semi-definite operators. And if alpha is between 1 and 2, then up to some constants, one can choose them to be negative semi-definite operators. These are not just some mathematical properties, they actually have uses. So for example, one thing that the Brown-Fauzi-Fauzi method can't achieve, but this one does, is that even if rho and sigma don't lie in the support of each other, the bounds one generates are non-diverging. So this is useful for device-independent advanced distillation, for example. Also, and this is a bit of a conjecture, I think that these properties might be useful for bounding another connected entropy, namely the up arrow Petz-Rényi entropy. So let's go back to the goal at hand. This was our original optimization problem. And for those that have been paying attention, I've been calling this the sandwich Rényi entropy, but then I've been talking about the Petz-Rényi entropy. But thankfully, the sandwich is strictly larger, so we can always lower bound it with the Petz-Rényi entropy. And now we want to lower bound this quantity. So let's consider the standard CHSH setup to see what happens here. So for those that don't know about it, although I suspect most do, we have 2 parties, Alice and Bob. They share some bipartite state, and an adversary holds some quantum side information. So now Alice and Bob apply give the device some measurement input. So they basically say what measurement they want to do. These are binary inputs. So X and Y are either 0 or 1, and they generate binary outputs. So we call Alice's outputs A, and Bob's outputs B. The private data that we want to generate is Alice's output A. For those wondering why this is asymmetric, usually for QKD protocols, we want Alice to generate random data, and then we want Bob to be able to reconstruct Alice's data. So there's where the asymmetry comes from. The public data are the measurement inputs. And also there's an additional test bit. This basically says, did a test round occur or did it not occur? So here, just for concreteness, whenever we say S is equal to this perpendicular sign, this is equivalent to saying that T is equal to 0. And also for the CHSH setup, T equals 0 means that Alice applied the measurement corresponding to X equals 0. So this quantity of interest is actually saying how random is Alice's output given that Alice measured with X equals 0, that measurement. And the test that we apply is the standard CHSH test. So it's 0 if X times Y is not equal to A plus B, and it's 1 if X times Y is equal to A plus B. So how does one do it? Well, one uses the MPA hierarchy. What this does is it generates variables, or monomials sometimes called, and basically one can replace the Petz-Rényi entropy with a linear function of these variables. And similar, the distribution P of S can be replaced by a linear function of these variables. So now it becomes a convex optimization problem. And now let's see what we get from this. So this are the results from Liu et al. This is basically the best version of the entropy accumulation theorem out there. And basically what they did is they calculated the following case. So they assumed that they win the CHSH test with probability 80%. The blue line corresponds to having a test round fraction of 1%. The red line corresponds to a test round fraction of 0.1%. And one can see already here, really sad numbers. You need always 10 to the 7, 10 to the 8. This is kind of the quirk of DIQKD. And now these are our bounds. So here, the main point is that when the original bounds are either 0 or very bad, this is when you see the most improvement. So here you see a factor of 3 improvement. And I should also point out that this is not the best version of the Rényi EAT. So one can actually improve this a little bit more. We just wanted to show that the simplest, most straightforward way of applying it outperforms the best thing that's known for entropy accumulation theorems. Also, I should point out that for those that don't like the MPA hierarchy or have never used it, there also exist analytical bounds for these expressions for the CHSH test. So there's a poster that I'll be presenting later today, and this makes life a little bit easier. Okay, let me just conclude by saying what I didn't talk about today, what can be improved on this, and then I'll be done. So first of all, the Rényi EAT isn't just useful for device-independent QKD, you can use it for device-dependent QKD, and also there you have also improvement on all other techniques such as entropy uncertainty relations and whatnot. Similarly, I didn't talk about the Petz-Rényi divergences, that they're also really useful for device-independent advanced distillation, but I should point out that advanced distillation in the DI setting so far only has security proofs against collective attacks, so one should keep that in mind. Also, so what can be improved? So at the moment, the single round quantity is the down arrow sandwiched in the entropy. For device-dependent QKD, one can turn this into an up arrow quantity, and one would ideally like to have this also for the DI setting, but for this one needs stronger chain rules, which no one has been able to prove yet. However, interestingly, there is some work in this direction. So for example, Amira Khan will present something on Friday on this, and so these are already very promising results that suggest that this is indeed possible. Similarly, if one manages to prove even stronger Rényi EATs, then one also needs stronger computational tools to go along with it. So here, one would ideally like to find variational bounds on, for example, the up arrow Petz-Rényi entropy, or maybe, if one is lucky, on the sandwiched Rényi entropies, which are much harder. And with that, I'd like to conclude. So any questions? These are the archive papers. Thank you for your attention.
Thank you, Thomas, for the very nice talk. Are there questions? Yes, one on the back there, on the other side. Is there no...
I have one question. So you are considering the device-independent QKD, but in the case of QKD, based on the observation, we need to estimate the channel parameter.
Can you speak up a little bit? Sorry, I don't understand.
Okay. In the case of QKD, usually we obtain some observed value, and based on the observed value, we need to estimate channel parameter. So that kind of analysis requires something like the estimation error, but you didn't discuss the estimation error. So I'm slightly confused.
So you're asking, so generally for the test rounds, the estimations there, or am I understanding that correctly?
Yes, so how did you include the estimation error in this, your discussion?
So if I'm understanding correctly, let me maybe go to the correct slide. So here the Q is where you kind of consider the test data and also estimation errors on this. So Q is not some fixed value. You kind of take your ideal test data and then you generate like a little set around this. And then you say kind of, as long as the distribution lies inside this set, then you're happy. So the way you generate it is via the honest behavior. This is the one that you'd expect. And you can do this as well for device-dependent QKD. The test is just slightly different, but essentially you create your the acceptable test data. You create some error bounds on this, which you generate just via the honest implementation, and that's where it's included.
Sorry, I cannot understand. So, what is the observed value?
So maybe we cannot hear if you could speak closer.
Okay, okay. So I cannot understand what is the observed value.
You mean the observed value in the test?
So because maybe you are considering a BB84.
So I hear this is purely for device-independent QKD, but
device-independent. Okay.
Yeah.
Anyway, you obtain some observation, observed value.
Yeah.
So based on observed value, you considering some system, but usually the system parameter is different from the observed value.
No, I mean what you do here is before the test, before you do the protocol, you say, okay, I only accept if I see a CHSH winning probability of 80% plus minus a little bit. Then you run the test, you do the analysis, you see, okay, 80% of the time I win. So you see it lies in that set and you're happy. So it's a predetermined set that you choose based on how well you know the experimental setup, right? I mean, you choose the one you know you can create. Then you run the experiment, and then the test data is literally just what you see, right? So you have 10 to the 7 rounds, you have 10 to the 7 different values of S. You write the distribution of what you literally see, and you see whether or not it lies in that set, basically.
Still, I cannot understand. Usually, you need to evaluate the estimation error, but you didn't consider that point.
I'm not, it's like, I mean, the error of the setup is just, I mean, you don't really care about the device-independent QKD. That's all incorporated in the expected test distribution, right? Like you can say, okay, the measurements have some error, maybe that generates some noise, the state has some noise, but that all culminates into a single distribution where you say, okay, how often am I really winning the CHSH inequality or CHSH test?
Even in the self-testing, we need to care about the estimation error, I think. By using the CHSH inequality. Of course, if you consider asymptotic analysis, so you don't need to care about that kind of estimation error. But now you are considering some kind of thing like a finite length setting. So in that case, you need to care about the estimation error.
Yes, and that's, so maybe I'm misunderstanding, but what I'm saying is that before you do the test, I mean, you've already worked with your experimental setup. You know what you expect kind of from it. So you say beforehand, I will only accept if I see a certain type of distribution. So before the test even starts, right? You say, okay, I expect some value plus minus a little bit. So maybe you're okay, like if the setup, you expect an 80% win rate, but you get an 80.5 or maybe even lower, then you're happy with that. Like that's all incorporated into this constraint of the test acceptance set. So here you really only care about the witness distribution and you set the set of the ones you'd accept beforehand. And you can generate that any way you want, right? That you say it from the honest behavior, this is what I'd be expecting, right? So you have your experiment, you see, okay, this is what I'd like to see, and then you work with that.
I cannot understand.
Sorry, maybe I suggest that we move on and you guys maybe discuss outside later.
Perfect.
Are there some last question? Yes, please.
Just a quick question. So I kind of missed what this event omega is, or and I'm wondering. So you described this as a lower order term. So does it scale with n?
So okay, I should watch out. Technically, it's only a lower order term, as like a second order term, as a function of how alpha scales. But basically, what one does is this omega is the probability of generating an acceptable distribution from some state. And you set this to be really low, right? So this is kind of like an unluckiness parameter. But typically for experiments, you'll say, okay, 10 to the minus 5, right? So it's saying if the outcome I'm witnessing or the accepted distribution I am hoping for, if that happens with at least 10 to the minus 5 probability, then you're happy, right? So this is where the omega comes from.
Right.
And then that's a fixed value.
Right.
The reason I say second order, and maybe this is a little bit not the correct way, is typically the alphas you choose to scale as a function of n. So as n grows larger, you want to choose alphas closer to 1. So what you do is you choose alpha to scale as 1 plus 1 over square root of n. So in the denominator, you have 1 over square root of n, and that scales as square root of n. So this is why I call it second order. In principle, for fixed omega, and for fixed alpha, that's an O of 1 error. So here, like, I mean, depending on how you view it. So here, the way I've written it, it's technically an O of 1 error, so it's not even a second order error. But if you want to really look at it similar in vein to the original EAT proofs, then they'll call this a second order error, because they have a specific scaling in mind for how you should choose the alphas.
And if I may follow up, what's the motivation of choosing alpha to scale with n?
So basically you want alpha to go to 1. I mean, then you get the von Neumann entropy. That's the single order contribution you expect in the asymptotic limit. Now the question is, how quickly should it scale, right? Like if you choose an exponential scaling towards 1, then the second term is not a second order contribution. So you kind of want to find the correct one, right? And it turns out that the one I mentioned is exactly good enough to get the asymptotic behavior.
Okay, great, thanks.
So let's thank Thomas again.